In the last video, we just learned how recurrent neural networks use a chain-like structures to make use of its existing predictions for improving future predictions. In these lessons, we will dive into its mathematical representations to see how this concept can be achieved. Let's get started. Let's take a look on the forward propagations. And the recurrent neural network uses the input x and activations value a to predict the output value y. At time step, let's take a look on the time step 1. The recurrent neural network will use the input value x1 here, the first value, and the previous value or the previous activation value, that is the a0, to predict the current values, that is the output y1. The parameter used for each step that is shared. So you can see that for the entire x input sequence, it will be governed by the WAX parameters, and at the same time, these WAX parameters will be shared for the entire AX sequence. And also for the WAA, it will be used to govern the horizontal connection from activations A0 to the hidden layer. But these WAA will be shared for this entire sequence also. And finally, for the output connections, we have WYA is being used to govern the DAP connections. And also you can see that WYA is shared for this entire output sequence as well. For the mathematical representations, we are going to take the input x1 and also previous activations value a0 and then multiplied by their corresponding parameters plus the bias parameters, and the entire things will be activated by a activation functions. Normally, it will be a 10h for this a value. And we will then have this a1 as an output, and this a1 will then pass along to the next sequence, but at the same time, this a1 value will pass along to the output for this y1 value, and this a1 will then multiply by the wya plus its corresponding bias, and then the entire things will be activated by the corresponding activations function. It depends on what kind of output that you would like to have for this sequence, and then it will help you to calculate the corresponding y1 value. More generally, at any time step, it will take the previous activations value at-1, and then and then multiply by the WAA, and then take the current input value and multiply by the WAX plus the parameters, and activates it by the corresponding activation functions. Just like what I mentioned, that could typically we will use 10h, and to calculate this AT, that is the current activation value, and these current activation values will pass it to the next layer, to the next hidden layer, but at the same time, for these AT values, we will then multiply by the WYA plus the corresponding bias, and then activated by the corresponding activations functions, and give you the current output value. So just like what I mentioned, more generally at time t, the recurrent neural network will use the input value xt and also previous activations value at-1 to predict corresponding output value yt. And these equations defines the forward propagations in the recurrent neural network. Sometimes this recurrent neural network has some problems because it only uses the information that is earliest in the sequence to make a predictions. But sometimes the future predictions might have some impact for the current predictions, especially when we are talking about the natural language processing. Some future works might help the predictions for the current verbs. In that case, bidirectional recurrent neural network can be used to address these problems. Sometimes it's slightly easier for us to combine the parameters WAA and WAX together to form the WAA1 for better representations. And the advantage of this notation is that rather than carrying two parameter matrices, that is the WAA and WAX, we can just compress them into one parameter matrix that is the WA, which actually can simplify the notation easier, especially for the more complex models. And similarly, for that notations, we can change the parameters WY8 to WY. So with these four equations, they will define the entire forward propagations for the recurrent neural network. Now let's take a look on the backward propagation. Similar to a typical neural network, for recurrent neural network to compute back propagations, we need a loss function. Let's define an element-wise loss with the use of cost entropy loss at single time t. For each time step t, we calculate the losses, but of course it's only used for the time step t, so for the entire sequence, we can sum up all the losses to calculate the overall losses. However, this is a very slow process, and also the gradients can easily blow up because the change in the initial conditions can potentially affect the outcomes a lot. Therefore, these strategies cannot be used in practice. Therefore, in practice, normally we will truncate the sum at a certain number of time steps instead of the entire sequence. This will help us to have an approximation of the true gradients. At the same time, the process could be speeded up, and also the gradients will not be easily blown up. In practice, this works quite well, and is commonly referred as a truncated backpropagations full time. One additional consequence is that the models now will focus primarily on the short-term influence rather than the long-term consequence. This is actually desirable since it inspires the estimates towards simpler and more robust model. And that's it for these brief introductions of the mathematical representations of recurrent neural network. In the next video, we will learn how to build a recurrent neural network. See you in the next video. Bye-bye.